be enjoying some good conversation over lunch about what we've all seen and heard this morning, but we should get back into it. So my name is Rosalind Archer. It's my pleasure to chair the afternoon session. I'd like to introduce our next speaker who will be joining us online. Sam Abraham is a Global Technical Advisor of Low Carbon Solutions at Halliburton. Over 30 years experience in the drilling industry, ta-da. Dual degrees in petroleum technology and engineering management. So he has a career that has spanned both oil and gas and geothermal, worked in numerous jurisdictions, Indonesia, New Zealand, Turkey, the US, Dominica, Kenya, Tanzania, Djibouti, Ethiopia, and the Philippines. So Sam is joining us by video, so over to you, Sam.
Thank you, Rosalind. I appreciate, and thanks to the Australian Geothermal Association for this opportunity to present to you all on behalf of Halliburton. And gives me great privilege, and having worked in that area before, pretty much almost 15 years back when we first started doing the habanero wells. So I had some experience there. So without much ado, I'd like to go into what I'll be speaking to you all this afternoon. So what Halliburton does is we always try to collaborate and engineer.
Sorry, Sam. Your sound is not coming through that clearly. So you're closer to the microphone, or
sure. I'll try to go closer to the microphone.
That's better, but even closer might be even better.
Fine. Let me try that. Okay. Can you all hear me now?
Go.
Okay, great. So what we do is we try to engineer solutions, mainly looking at challenges that our customers face, how we can drive those solutions that we engineer, and collaborate, especially looking at the life cycle of a geothermal well, which is quite different to oil and gas wells. Oil and gas, if I can get my oil in 5 years' time and walk away from that well, I'm the most happy person. Geothermal, we are looking at what we have, for example, across the ocean in New Zealand, where we've got the early wells at Contact Energy since 1958 and around that time. So that's what we look forward to in terms of geothermal wells, and when you mention life of a well. So I would like to cover these agendas that we are looking at up on the screen. I wouldn't waste time going through each one of them, but let me go to my first slide. So I took the privilege of using Pollack's paper that was published in 2021, which went across about 64 sites globally who had done EGS projects. And then I sort of narrowed it down to some of the wells that have been drilled in Australia since 2010. And I had the privilege of working that time with the late engineer Steve Pye on the early habanero wells in terms of planning, some designing, and also some reviews on how they worked out. So I looked at the challenges that we faced, and overall what we see in EGS wells is drilling operations, maintaining the well integrity of a well. Many times drilling these deep wells, you have stuck pipe issues, lost in oil equipment. Then sometimes it was also a challenge was the operational rating of these equipments. The other thing was overpressure, well kicks, and mud losses. Corrosive brines in some areas, which could lead to sulfide stress and other cracking, which affects the metallurgy of these casings. The other one was, how do we create reservoirs, especially with high temperature, high pressure simulation? Again, when sometimes you create them, there's still only a negligible increase in injectivity. Then some of the challenge was, you would expect a few different structures, but a single fault structure. So the potential of recoverable heat was pretty reduced. Modeling challenges, as Jeremy was talking just before the break, the quality of the logs that we have, how do we interpret them? How do we first prepare a conceptual model, and feed in data after we drill the wells to refine them. And the last of all the challenges was regulations and financing, the upfront cost, and the risk mitigation that was to be done in order to prevent cost overruns and also grid connectivity. These are the challenges that we faced. And this was about since 2010 when we first started drilling those wells in Australia. What we did, what Halliburton itself and some of the other technology partners have gone through about 15 years of iterations trying to solve these problems and how can we drill these wells better. And from a practical aspect, having worked across, one is the Forge project and some of the projects in Newberry and also Mazama, where those are a few of the new projects that are going on. And what Halliburton has done is trying to use our technology, how we can refine them to better achieve targets. So here, if you look at the first part was well designed, and I would be speaking specifically on drilling and pumping technologies. I would not be going into much into logs and subsurface. So here on the surface, what we were looking at, how do we design these wells? Mainly to mitigate the risk that's involved and also optimize drilling, which is again helps us to, as we optimize drilling, time spent is reduced and that in turn affects the cost of these wells. Landmark is one of our main product service lines where we use well planning based upon WellCat and WellPlan softwares to be able to better design these wells. Also, some of the subsurface insight that we get helps us in planning these wells better. Also, when we drill these wells, as we go from one well to the other, we do a lot of logging where we gather data and using that data, for example, what Sequent was talking about, initial construction models are there, and then as every well is drilled, we put that data back into the model to refine this model. That's what's the well design part of it. Now, as time has gone by, early enough in the early 2000s, there was a lot of challenges with drilling fluid management. The drilling fluids, as you drill through low temperatures to medium temperature are fine, but as they go into the higher temperature regimes, they start losing their properties. So here we have worked a lot on how to deal with high temperature. Second is treating losses, which are quite critical when you drill the upper section of the well, because if you do not cure the losses, then drilling and getting to TD plus running casing and cementing them becomes a big problem. The third was very important part of it is hole cleaning. Many times there's a big push going on how fast can I drill, but at the same time, using the drilling fluids that are there as a circulating medium to be able to clean the hole, lift the cuttings out, helps us to prevent further problems if we do not get the hole clean. The other challenge was differential sticking, where you've got different pressure zones in the well, and if losses are there, the drill string tends to get pulled across to one side of the well. The last of it is casing of cuttings and waste management. Many a times we have seen that nowadays we see there's a lot of this type of drilling in EGS wells happening in very close proximity to big cities or human settlements, number one, or in areas where the environment regulations are quite strict and you have to manage your waste properly. So Halliburton has now come up with a waste management system where we gather the cuttings, take the fluids back into the pits. The cuttings are almost sieved out, pretty much dry. They can be then sorted out to get you the cuttings, which can be used sometimes on your rig sites, or if they have got some heavy metals, they have to be taken to a different dump site. Why is this quite important? I'll give you a very simple example. We drill in Philippines, very close to villages, and if the mud is not dry, the mud sitting over time tends to have bacteria acting on it and has a very foul smell. You cannot take those cuttings through a village that's there. So a couple of the new products that we have made is one is called Bara Extreme, and the LCM loss circulation material. We heal those losses using Bridge Maker, where if you see on the right side, you see the dry solid, that's a black color item. And then once it mixes, you see how it forms almost like a plug on the right side, bottom screen. This is drilling fluids. Third thing is in drilling, especially as we were looking at some of the new EGS wells that are being drilled, you are going away from your vertical wells that you were drilling to pretty deep angles or high angles or even to almost horizontal drilling. Here again, that's one part of it. The second part of it was the placement of the wells, which was very important. If the wells were not placed properly, if their spacing was not done properly, the final plan of each of these EGS technologies runs into trouble. And then we also have the ranging technology where you were trying to meet two well bores together so that they could intercept and that could form a conduit, for example, like what Eavor does. So here we've come up with some really intelligent rotary steerable systems, which help in the durability of these tools, as well as working in quite harsh environments. The other one is MWD and LWD services that we have. They help us to get much better precise targeting, number one, understanding the pressure while drilling, because sometimes high pressures, you have to deal with them. And then also the triple combo, which helps to get us data as well as telemetry. Last of all is magnetic ranging. This magnetic ranging is quite important when, as we saw earlier, wells are being drilled parallel to each other, have to maintain a very complex geometry and be accurate and have to have efficient intersections. That's what magnetic ranging, one of the new technologies has been developed, is being used for. As we go through the next one, the bigger challenge. The deeper we go, more high temperatures that we intercept. You have mud motors. Earlier, these mud motors used to have elastomers. They would not last through these hot sections. So now we've got metal-to-metal power sections, which help it to go through higher temperature zones. Then we've got, again, it helps to reduce torque and drag, because once you go into those sections which have got very high angles, the challenge becomes the torque and drag. That could actually cause us problems when we're trying to move a string and also get stuck at times. Last of all is optimization. Here you're trying to optimize the time that you take to drill these wells. Optimizing helps us to reduce cost in the other way. And the last picture that you see down below on your right-hand side to the bottom is what we call a continuous circulation system that we have developed. What does this help us? It helps us to reduce the temperature when the hole is not circulating during the pipe connections. That's number one. And that also helps to keep the cuttings in suspension, because the moment you stop circulation, the cuttings start to drop down around your BHA, and it drops down around the biggest sides of your BHA, and you can tend to get stuck in those wells. The next one, very important, the first thing that sees the formation is your drilling bits. Initially, if you were 20 years back, if somebody was to tell me, hey, Sam, I'm going to use a PDC bit, or if I was to tell somebody, people would say, Sam, no, we are not using PDC bits. We'll stick to our roller cone bits. But now, with technology improvements, we've come up with really very appropriate designs on the number of blades that you have in these bits, where you place the bits to be drilling in gauge, the number of blades that you have, the side loading on these bits helps us to take care of the impact resistance, especially when you are drilling through very hard formations. These are quite important to be able to take care of drilling one section with one bit. What does that save? Again, our time that we waste, that we spend on tripping. That's a part of the non-productive time. And the last picture that you see there down below, the green color bit, that is one of the latest technologies that we have added. This actually has a sensor right at the surface, just next to that red dot, red color piece on the shank. What does that give us? That gives us a place where we place sensors that's recording all the data like temperature, weight on weight, RPM, torque, right at the bit surface. Currently, these are only in memory mode so that you have to drill them. Once you pull out, you can get all the data downloaded. And what does that help? Helps us to design the bits. And nowadays, we've actually come up with bit designing where we can turn around in about 4 weeks' time with a new bit design. Going from there, after you drill a well, after you have drilled a section of the well successfully, the most critical part of it is you have to cement these wells. Otherwise, the integrity is lost. Now, cementing these wells, maintaining the well integrity for the life of this well is quite critical. So there, what we have come up with a few new things are thermal ox cement, which is there helpful in very high temperatures, and also it takes care of challenges like corrosive environments or brine as things. Then we have come up with a non-Portland type of cement alternatives, which is a little bit lower in cost, yet helps to match the same less strength restoration as time goes on, gives us better corrosion resistance, helps with thermal cycling, because many times when we have these wells flowing, at times once in a year or once in 2 years, you have to work over these wells. At that time, you have to take these wells offline. So the casings shrink first, and then you have to put it back online, the casings expand again. So that gives a challenge of thermal cycling. And this type of cement helps us with that. We've also now gone to a corrosive cement type where we are adding crystalline silica to be able to give it better strength restoration and also low permeability. And if you see the last picture down there, or the first picture to your left, you see the traditional way was pumping down cement down the drill string, taking returns up the annulus. Now we have come up with better processes where we're actually pumping cement down the annulus and taking string returns back to the drill pipe. What does that help with? It helps to maintain hydrostatic pressure at a lower pressure so that it does not fracture the formations, and helps to fill lost circulation zones. We've even added foam, which is actually nitrogen, to be able to go and give better compressibility so that they can fill the gaps better. Now, some of the new technologies that we are now working with, they are still in the process. They have not been completed, but that's why I'd just like to share something. One is alternate rock removal technologies. We are trying to find different methods of drilling through the hard rock, drilling deep into the earth in terms of depth. How do we improve the hole cleaning when you're drilling at 5,000 meters depth rather than 2,000 meters? How do you maintain proper ROP? And the last of it is maintaining the hole geometry. This is being developed by different technology partners around the world, millimeter wave, plasma. But these are all emerging technologies, are being tested now. And probably in the next 2 to 5 years, we should see some breakthroughs. But currently, they're still in the process of working together. As I come to the last one, conclusion-wise, what are we looking forward? What have we achieved in the past 15 years? And what are we looking forward to? We've taken these steps to understand the risks that are involved. How do we mitigate these risks? That's the first part of it. Second is, how do we improve drilling efficiency? The moment you're improve drilling efficiency, that helps us to get better results in terms of drilling or in terms of cost reduction. And the third is subsurface modeling. That's what Jeremy and all do, but these all play together. We all have to play together as a team. The first one is, one of the very important things is when we reduce our survey times during our directional drilling, it helps us to reduce stuck pipe issues. Because the moment you stop your string motion, that's the chance of highest stuck pipe issues. The second thing is, with the changes in the density of cements that we use, we've been able to get better cement coverage around the wellbore, both in the casing to casing section and the casing to open hole section. And they have helped us to get better compressive strength and to deal with higher temperature formations. Nowadays, we use a lot of fiber optics, because nowadays when we are placing wells very close to each other and having to monitor across these wells, the fiber optics are really helping to better gather data, improve the modeling, and help a lot in simulation practices. Then the drilling fluids that have been developed help us with dealing with losses, and especially also drilling through high temperatures. And then cooling the mud. It's very important. This fluid that's going down gets heated up. If it's not cooled down properly, what happens is it loses its properties and goes back to, it becomes useless. So we take a lot of effort in maintaining the mud cooling system, both downhole and on the surface. We've got mud coolers, which help to get a pretty sizable drop in the delta T as it goes from mud out to mud in before it and goes back into the well. Last of all, borehole imaging. Sometimes when we've got losses, we cannot really get a lot of data. So we've developed some tools to be able to get better images, formation images from the wellbore, so that you can look at the fractures and other things in the wellbore and design your wells properly. Last of all, GeoESP pumps. Some of these wells need to be pumped, fluids to be pumped down. And on the other hand, in production wells, you need to suck the fluid out because they may not flow on their own. So we've actually developed geothermal ESP pumps so that they can be used to pull the fluid out and then take it up to your surface facilities power to generate power. That's my presentation, and I thank you all for listening to me and to the opportunity to given to present on behalf of Halliburton on what we have done in the EGS field in the past 15 years since we started drilling first in the EGS projects in Australia. Thank you very much. Appreciate your time.
Thank you, Sam. Are there any quick questions in person, online?
There is a question from Ella Maria Llanos. With all the drilling advancements you've shared, what changes would you recommend should another well in the Habanero field be drilled?
Okay, thank you. That's a pretty good question. And I think so that sort of covers, gives me so what would you do different compared to what we drilled before? Especially if you would look back at the casing designs. How do we set these casings? How do we design the wells? That's quite important. Number two is the bits that we would use. We would look at better PDCB technology, which can help us to drill these wells better. The third thing would be drilling fluids that we would use, because last time when we were drilling, we had some kicks in these wells, and we would use fluids to be able to better manage these wells in terms of density as well as losses in those zones. And the last would be cementing these wells. Very important, so that you get good cement well integrity in terms of formation and casing interaction. Otherwise, they tend to damage the casing in the long run. And then the ESP pumps, the submersible pumps, can be used if these wells do not flow, to be able to pump these fluids from the wellbore back to surface and take it to our power plants. Thank you very much.
Thank you, Sam. Okay, well, I think we should thank Sam again for his presentation and move on to our next speaker. So our next speaker is Kifayat Hussain, who's Geoscience Business Manager at Schlumberger, with years of hands-on and production. He has a background in subsurface evaluation, resource assessment and reservoir characterisation, applying a great number of applied techniques to unlock geothermal resource. So, over to you.
How do I push to the next slide? So just back and next?
Yeah, just those areas.
Those three lines. Perfect. Good afternoon, everyone. Thank you for having me here. I'm Kifayat. I was just introduced. I'm the Geoscience Subsurface Business Manager for Australia, and I'm based in Perth. I've been working predominantly about 23 years of my life, 24 years of my life with the oil and gas guys, but I have worked around and transitioned with mining, the coal seam gas space, etc. So we don't have much interactions with geothermal companies in this part of the world, except for Indonesia and the Philippines, for example. So I'm going to show you some snapshots of examples from there. And I've also got a case study that I'm going to share with you once I come down to the basics of how do we actually characterize our reservoirs, because characterizing our reservoirs is really important to de-risk our projects. So, perfect. Now, when we look at the geothermal project development cycle, we usually go through several phases. We've got the reconnaissance exploration, pre-feasibility, feasibility, and development drilling. But when we look at the underlying processes or the domain expertise that need to be developed around these processes, we can broadly characterize them into wellbore interpretation, subsurface interpretation, fracture characterization, along with building the static model, identification of the sweet spots, and dynamic model or dynamic simulation, and also focus on well placement and stability analysis. So I'm going to first dive into, I've kind of simplified some of these slides just to kind of make it simpler for the audience to kind of understand a lot of what we're going to see here. But in the wellbore interpretation part, we have different data types that we actually receive from existing wells and even new wells that we're going to be drilling, whether they're new exploration wells. And a focus over here is that we predominantly acquire log data. That log data is important because that will help us identify lithology and mineralogy of the formations that we are targeting. Apart from that, we can also focus on interpreting FMI data or formation microimaging data. That formation microimaging data will give us information around bedding planes. We can pick fractures. We can understand the orientation of those fractures. And apart from picking the dip and strike information of those fractures and those bedding planes, we can then create stereo nets, etc. Now, on the right-hand side, we have a graph which is a downhole summary plot. And in that downhole summary plot, we also have temperature curves along some known well locations over here. This is from an area in Taiwan where we have a thermal plume, and we can see that temperature plot, and within that particular area, you actually see a stereo net plot, which gives us the preferred orientations of the fractures and the faults in that particular thermal plume zone. So with all of this information, we can also start developing what we call a one-dimensional geomechanical model or a mechanical earth model, and that will then feed into our borehole stability analysis, which we will look at later on. And of course, once we have understood all of our fractures and identified which ones are permeable and which ones are closed, we can then start looking at ranking that information. So if we look at the subsurface interpretation bit, of course, at this phase, we usually look at the basic geochemistry of the field. We start developing our 3D structural models. We actually model properties like porosity, permeability, map out our facies, populate that in our model. We also proceed to create a 3D temperature model. And of course, doing well correlation based on the borehole data that we have, and also combining geophysical interpretation techniques, whether they're purely seismic based or even non-seismic based methods. So all of that will help us to refine our subsurface interpretation, which will then feed into developing our static model and also characterizing our fractures. So when we look at this particular flow chart over here, we start off by characterizing the fracture data that we have in the wells that we've already got drilled in that area. We can then go on to building a three-dimensional fracture model. That fracture model can be further subdivided into that portion at the top over there, where we can start to characterize whether the fractures we are seeing are as a result of damaged zones or if they're related to bending, deformation within the strata, or if they're related to any particular fault features that we're seeing over there, whether they have any influence based on the tectonic model. And we can also see if they've got any relationship with any intrusive features. Now, those last two images in the top section of the slide there do not apply predominantly for Australia, but they are very common, for example, in Indonesia, where a lot of the geothermal resource is related to an intrusive body. And in that case, we have to have a look at whether there's any fractures that are a result of cooling effects or maybe even pressurized intrusions. Once we've characterized our fractures, we can then go on to building a geological model. And once our geological model has been built and we have actually upscaled and modeled in our properties such as porosity, permeability, temperature, etc., we can start playing around with various variables to perform an uncertainty analysis. The uncertainty analysis is important because that gives us a range of estimates for the kind of resource we are actually dealing with and drive our resource estimation based on it. Sweet spot identification. So once we do have our discrete fracture model built, and we've modeled in our temperature and thermal properties in the geothermal reservoir, we can then start to run a Monte Carlo simulation, simulate multiple realizations of each one of those individual properties, and then a combination of that information will allow us to create sweet spots maps, and these sweet spot maps will actually provide preferable locations for geothermal targets. Now, another very important thing is, as we're moving to more and more deeper geothermal reservoirs, most of the reservoirs within Australia are well below 3,000, 4,000 meters. This requires some advanced drilling. It also requires us to start thinking about horizontal well placement, etc. That means having the ability to actually steer our wells within those horizontal targets. And for that, our main focus again over here is using technology such as spectral gamma ray, what we're seeing in that lower image over there, that gives us an idea as we are drilling through these reservoirs, whether we are still on track within these reservoirs. Do we need to steer the well up or down or laterally? And the spectral gamma ray, for example, in this case, gives us a very quick insight into that. So what we are trying to do with accurate well placement is trying to maximize productivity by navigating within the geothermal reservoir. And then, of course, comes wellbore stability and operational risks. So building 1D geomechanical models or mechanical earth models based on just borehole data, and then also building three-dimensional mechanical earth models is really important because we need to understand the trajectories that we are planning through these formations, how mechanically stable those trajectories are going to be. We can then couple that information with hydro, thermo, and mechanical models to see what is the impact of production and injection in these wells. In a lot of cases, one other important thing to understand is if we have, if we're going to be drilling through faults or we have existing fractures, whether those fractures or faults will be reactivated by this production that we are actually going to be inducing in that scenario. And another thing is subsidence and uplift is also something that we would like to take into account. Now, as we are drilling and we are actually producing stuff, we would also like to know if there's going to be any induced microseismicity at the reservoir formation that we're actually going to be tapping into. So these become important building blocks. Now, more and more over the years, this is not something new. Multiphysics data has been around for quite a while. This is purely a non-seismic based way of working with some of the data that we traditionally find, such as gravity and magnetic data, magnetic tellurics, which can be then combined with some kind of a simultaneous joint inversion process and combined with gravity, etc., to have a more accurate depth image of a particular formation that we're after, or even the basement that we're after, and then even things like microgravity. Microgravity is important because that gives you a time lapse. Microgravity is a fairly new technique. It uses very, very sensitive instruments to monitor gravity, and you can actually run these over time, again and again on the same area, maybe a time lapse of 5 years or 10 years, and what that will give you is give you a way to kind of monitor how the reservoir's characteristics are changing as you're producing from them. So again, I didn't go into each one of those bullet points, but the whole idea is that you're using all of these multi-physics-based data sets to kind of control how your structure is actually controlled within the area. It'll give you an idea about where your faults are. For example, you could take the magnetic data and you can pick lineaments, etc. That'll give you a better way to constrain your model. And then also joint inversion of these data sets, such as magnetic tellurics and gravity, will give you a very good control over the properties that we're going to then model into our structural models. So that was just a bit of a background that I wanted to give there. I'm going to start by diving into a case study. This is a case study. There's actually two published papers on this. SLB was heavily involved in this. We had the geological survey of Northern Ireland involved in this, and we also had the Department of Economics that was actually involved in a lot of this study. And I'll get into the details of that, but the whole idea was trying to understand the geothermal potential of Northern Ireland and trying to understand how we can use that information to guide future exploration activities. And the case study is kind of unique because we have to look at integrating and interpreting multiple data types, not just traditional seismic, but gravity, magnetic, etc., to build an accurate 3D structural model for the area of interest. So diving into a bit more detail over here, the area is Antrim in northeastern Northern Ireland. It's very, very close to one of the famous lakes over there, Lough Neagh. So the Lough Neagh Basin was identified to be a really good prospect for deep geothermal reservoirs. The Sherwood Sandstone Group is the main target over there. It's mainly Permo-Triassic basins, and on the shallow part, there's a lot of basalts over there. So the basalts actually tend to be a challenge because they actually degrades the seismic quality. There's other issues around that area, which is we have the town of Antrim right next door. We have the airport, the Belfast airport is near there. We have the lake, so there's some conservation concerns over there. And there's a lot of farmland, a lot of heavy traffic roads. So acquiring seismic data in an area like this is going to be slightly challenging. So here's just a quick plot of all the data that was available within that area. Some new data was acquired in 2023 in that red kind of polygon area. That's a 36 square kilometer area. And basically, initially they had 4 seismic lines that were available. Those black lines on the map actually represent the 4 seismic lines that were available in the area. Those red dots that we see there are actually the 4 wells that were available in the area. Unfortunately, none of the wells, except for one, basically intersected that seismic line over there. So you didn't have much calibration information to go around with. You have all of these different land gravity measurements which are represented by the black dots, and there's some legacy gravity points which were fairly old data sets from the 1960s, 84, and even 1990. 3 new seismic lines were acquired within that particular polygon of interest, which are indicated by the green lines, and you actually have that blue polygon area where new magnetotelluric measurements were actually acquired. So it was a big blend of old data, new data. We had very little funding for new data to be acquired within this area, but the whole idea was trying to come up with a solution to all of this. Now, this becomes slightly complicated, but I'll try and simplify it. But basically what we're doing is that with all of that field data acquisition, where we started off with the few seismic lines that we had control over, the magnetotelluric data that was available, and the gravity data that was available, we had to come up with a complicated process where we have to use the seismic time processing methodology to do a depth imaging, but then also use the magnetotelluric data to model that and generate an inversion, and use that information to further refine the horizons and the faults that we could identify and interpret within that area. Of course, we had gravity data which was available. So on the gravity data and some magnetic data which was available, we were able to pick lineaments, etc., which we consider as a potential field workflow. And using that information, once we built the preliminary 3D structural framework, we then used the potential field data, which is gravity and magnetics, and the magnetotelluric data to further refine that structural model. So here, for example, is also a very quick representation of the different images you're seeing. You can see the initial model that was built on the side. That was just basically a seismic depth image using interval velocities, etc. And over time, as we added in the magnetotellurics, use the inversion information, we could further refine the features, couple that with gravity and seismic and joint inversion. We had a more density controlled update, and then we had a geological update where we actually went in and picked all the faults and horizons that we could identify there. And we also applied some short wavelength tomography and post-migration to kind of remove any residual flattening and also denoise the data. So I know this is a bit of a mouthful, but in the end, the 3D structural model, where we started off with very, very limited data, very poor quality seismic, as I mentioned earlier, because we had basalts in the shallow part, which actually degraded the image, but then combined with all of this magnetotelluric data, the gravity data, joint inverting the data, we were able to get a much better image of the seismic, where we could actually guide a proper interpretation of the faults and the horizons, and then use that information to finally build our structural framework. And this structural framework then becomes the basis of populating properties like temperature, porosity, permeability, etc. So the key here is that this data was always available. Even in Australia, we have a lot of gravity and magnetic data that has been acquired by mining companies over time. Gravity and magnetic is really simpler to acquire compared to seismic, because a lot of it can be done through airborne surveys. But the potential here is that you can actually combine all of these different data types to come up with a much more accurate representation of the 3D structural model. So basically what we're trying to pitch over here is running a multidisciplinary geophysical and geological modeling approach, where you could take all of your geology, your geochemistry, and your geophysical data, start with an initial conceptual model. You could model things like temperature, or you could use your formation micro-imaging information to pick up your fractures, etc., pick up your the fractures that matter the most, update your model. You could actually forward model that data and those results to give you a more robust and more accurate model of the reservoir that you're actually targeting. And then once you have an accurate three-dimensional geological model to work with, you can then think about getting into a proper well placement optimization strategy, where you now know exactly where your fractures are, you know how your permeability is playing, you know exactly where your fluids are going to flow when you start to produce and inject fluids back into the ground. And you can actually evaluate uncertainty throughout at each particular proposed well location. And you can run that through a flowchart where you can actually divide that into domain work and automation. You've got the structural model building, the fracture data analysis, the model drivers which will actually affect your or impact your model, such as how are your fractures oriented, what is the aperture length, what is the aperture mean that you're actually having to deal with, and you can run Monte Carlo simulations, etc. You can have and understand the sensitivity of each one of those parameters to come up with a better result, and that allows you to screen the exact locations which could be the best targets for you to drill these wells, and how you would then use that information combined with your geomechanics, etc., to plan the wells properly so that you have a much more stable operation. So in a nutshell, I think I'm close to 15 minutes here. In a nutshell, get the most out of your data. All right, there's a lot of data available in Australia. The cool thing here is that we have a lot of public data sources. Offshore data is all available from Geoscience Australia. Onshore data, the Queensland government has a repository that you can tap into. South Australia government has a repository that you can tap into. The Western Australian government has a repository that you can tap into. You can get access to seismic. You can get access to all of these gravity magnetic measurements. You can get access to existing well logs, etc., from existing holes that have been drilled. I know it's kind of frowned upon because we are using a lot of oil and gas company information, but the reality is a lot of that information is available. It's in the public domain. We should use it to our advantage to kind of come up with a better understanding of the model in that area, because that will then help us understand what our drilling challenges, etc., are going to be moving forward. Right? So once we've built the 3D models, you can then use that to optimize your production, create a proper field development plan, and also take into account any uncertainties and even the risks that may be involved. So the key message showing that previous workflow again was that subsurface imaging has come a long way in the last couple of decades, not just now, not just today, but over the last couple of decades. And we have a lot of different methodologies in which we can actually reduce your risks when you're drilling And all of that should be taken into account, especially when we're going to plan wells or plan on developing a particular field. So all that information that I've presented is accessible at our geothermal page on the SLB website. And that's about it for my presentation, and I'm open to any questions. Thank you.
Happy to open it up for questions for Kifayat. Any questions online?
We've got a question from Evelina, and she's asking, for temperature models, what data do you use in the absence of wells?
Well, in the absence of wells, I mean, which is pretty abnormal because you have enough wells. I think even in Queensland, we had like 20, 30,000 wells just in the government database. And there's always temperature information available there. But you could use literature and you can get temperature gradients for different parts of the world. You could actually start by doing something like that. You always have surface temperatures. At least you could have that as a start. But you could also use analogs from similar sedimentary basins as a start. And use that to do that. In some of the modeling softwares, you actually have the ability to stochastically model temperature based on a few measurements. So it's not difficult to come up with a temperature curve from literature and actually use that to model stuff like that.
I'll pass your mic.
Thanks, Kifayat. How far off are you from being able to use real-time drill data as you're drilling a well to try to update and improve these models and sort of influence the particular well path in real time?
I came in not wanting to talk about any services or technology that SLB offers, but yes, we have the technology. We call it modeling while drilling. And basically, during our well placement activity or geosteering, we actually have tools where we can actually take measurements and plan ahead of the bit. We can on the fly update our static models or our structural models and our dynamic models and very quickly simulate. So for example, if you were expecting a certain type of porosity or permeability range, but you're not seeing that because the well is not steering in the right direction, we can very quickly, accurately do that. So we actually have technology we call modeling while drilling, but I didn't want to talk about that.
Does that require you to collect specific kinds of data?
Yes. We have certain tools which are designed for that, and it's a commercial service. We have a real-time operations center in most parts of the world. There's actually a team in Perth that focuses on that. Thank you.
Okay, thank you again. We better move to our next speaker, James Heatherington, who's joining us online. James has 35 years of international energy experience. Like many speakers, has started with a background study-wise in petroleum engineering. He's worked for IHS Energy in Tokyo around projects involving country entry, LNG, exploration, development, M&A, geopolitics, and energy economics, and describes himself as a long-term Yokohama resident. He's been with Eavor since 2018. So over to you, James.
Okay, thank you very much. I appreciate that. I'd like to thank you for the invitation to this series of seminars. I've been very impressed with the speakers thus far, and I've learned more than a little bit. So today I'd like to talk about advanced geothermal systems, and especially what my company, Eavor, is doing. Now, we were founded in 2017, and we actually started to acquire employees in about 2018 when I joined. And our idea was to take the technology and the business practices from the unconventional oil and gas revolution and then move that into what was in 2017 a fairly conservative geothermal industry. Now, as you know, the unconventional oil and gas revolution, it changed the United States. You took United States which was importing LNG, and changed that over the next, say, from 2000 to about 2010 to a country that was actually exporting LNG. And I know that you've also had unconventional gas plays in Australia, which have been very prolific. Now we're doing pretty good so far. Over $412 million in equity raised. And what we're using that money for is to develop our technology, to develop it further, to roll it out, and then actually test it in projects, in field projects around the world. We did have the presentation earlier today on finance, and I'd like to say that for our first project in Garrett Street in Germany, we've actually got the banks to pick up and invest in us, not as a new technology project, but as a infrastructure project. So we've gotten grants and debt financing from the banks. We've got additional grants from governments who look at our technology. They do their due diligence, and they accept that what we do and what we're trying to do is very real, and they buy into our vision. And what we're trying to do is to roll out geothermal so it can be used anywhere. Now let me talk a little bit about the geothermal universe here. You've seen this slide or very similar slides before, I'm sure. On the right-hand side, you've got very traditional systems, hot springs, direct flow, and what you see a lot in conventional geothermal provinces, doublets. Now moving more into the AGS side, we see EGS, and I'm sure that we're going to have some more discussions about what our competitors are doing in the United States, where you've got some sort of direct flow or frac flow between the two vertical wells. And then you've got closed loop systems, and we did have some presentations on that. Ground source heat pumps, or what Greenfire does, which would be pipe and pipe. But what we do is, we've got our closed loop system, and we've developed different flavors of this: Everlight, Everloop 1.0, Everloop 2.0, and then what we call Everjoules, and I'll talk about that shortly. But these are the different kinds of geothermal, and obviously I'm very much in favor of our system, but I'd like to point out that a rising tide lifts all boats. So if anybody is drilling geothermal, trying to change the laws, get the banks to fall behind projects faster and more efficiently, hey, it's one industry that we should all be rowing in the same direction. So I'll talk a little bit about what an Everloop is. So multilateral, and we have to go multilateral to be able to access this very diffuse resource that we're trying to get at. So first thing we do is we drill 2 vertical wells, case them and cement them using traditional methodologies. And then we drill a series of laterals, either horizontal or at an angle, and connect them up. We case the vertical sections and the kickoff, but the laterals, they're open. So we actually have to seal them with a proprietary system that we've developed. At the surface, we've got a heat exchanger, and we can take power off or take electricity off using that, or heat. And then we pump cold water, or just let cold water fall down one side. It flows naturally into the different laterals. It heats up, and it actually rises without pumps, without any extra effort to the surface using a thermosiphon. Then we use that difference in pressure, the difference in heat, and then we can do things at surface. So either we can use that to run a ORC binary engine, or we can provide heat to heating networks, or preferably to do both so that you can get the shared economics of doing one at one time and doing another at a different part of the year or a different part of the day. Now, because this is a closed system, there's no need for a permeable aquifer like you see with traditional geothermal. So you're not looking for fractures or permeability. you're just looking for the presence of heat. There's no fracking required, which is beneficial, especially if you're fracking or if you're trying to put these in place near cities or in places where there's tectonic stress occurring naturally in the rock, because you don't want to kick an earthquake off. Minimal continual water use. It's not 100% closed system. We do have very, very slight leakage to the formation over time, but that can be usually topped up, by a truckload of water every couple days or every week or so. But the most attractive thing is that there's very little uncertainty in the project. Once you know what the heat gradient is, once you know what the cost of drilling will be, then you can actually predict what the economic return of a project will be even before you start drilling. And this becomes, a different paradigm. Rather than dealing with exploration risk, you're dealing with manufacturing risk. So it takes it quite a ways from traditional geothermal or traditional oil and gas, where you don't really know what you're going to get until you start to drill it out. Now, this is what a Everloop can look like. We've got 3 different flavors that you see on the screen right now. Everlight was actually our first technology field test in Canada, and I've got another slide on that. After we completed that one, we drilled a Deep Rock 1, our first ever Loop 2.0 in granite in New Mexico in the United States, to prove that we could do cased hole kickoffs successfully in granite, and that we could drill fast in granite. And then we're drilling our first 1.0, Everloop 1.0 project in Europe right now. So that's going to be our first commercial project, and we are very excited about it and learning lots and doing lots, developing technology, proving our current technology as we do it. But more so, we really want to focus on the idea of geothermal anywhere. And we're developing a new suite of technologies to enable us to go down to extremely deep areas of the earth, almost to the ductile, brittle transition zone. And that will end up being probably one of the limits to geothermal anywhere. It's the ability to maintain stability of the wellbore, even though you might be looking at the brittle ductile transition at depths of, say, 10,000 meters or deeper. We're very looking forward to some of the first field tests of this new EverJoules technology, and you'll be hearing more about it in the next couple of years, especially as we do our first field tests in Alberta. Being able to do this will enable energy independence for countries small and large, energy security, which is a big, big topic nowadays, especially with the change in the world political environment. And then, of course, decarbonization, both for power and for heat. But our first project, now, when we first started in 2018, a lot of people said it couldn't be done. It was impossible. The idea of drilling down and intersecting at 2,000, 2,500 meters depth, a lot of people said it couldn't be done. So what we did is we built what we call Everlight, just north of Calgary in Canada. We went down 2,400 meters, drilled 2 laterals over, and then connected them up successfully. And this was all done on time, on budget, and with no health, safety, or environmental problems. It also went from idea to actually commissioning in probably just over a year. So we're pretty proud of that we could not only show that our technology works at field level, but that we could actually execute the project as planned. We operated then this Everlight for about 4 years. We used it as a technology test bed. and we used it to show that our algorithms, that our simulations works. We predicted what would happen, when you turn it off, when you turn it on, what happens if you get a sudden load to the system. And the actual behavior of the system was as we predicted. And so we were pretty happy with that. We achieved our technology objectives. We drilled and intersected at a very deep, at a very deep depth. We pressure tested our technology of rock pipe, and we showed that our thermodynamic simulations, that they worked as expected. We've actually had these validated by third parties as well, and those third-party validations are publicly available. Now, not only do we have the idea of bringing in more oil and gas technology into the geothermal industry, but we've also developed our own proprietary products. Now, some of these are just in-house systems and ideas and methodologies that we're using. Some are actually patented, so you can just use Google Patents to track these down. The open hole section, the laterals are of an Everloop are completed over open hole. So we need a way to seal them off to prevent fluid from going either into the formation or from coming out, not only during drilling, but during production as well. So we developed a system of chemicals we call rock pipe, and that's used to seal off the wellbore. It's not just one chemical, but it's a series that we run, and that has been proven now not only for Everlight, for Everdeep in New Mexico, but in the first set of wells in our Garrett Street, Germany project. We developed insulated drill pipe so that we could drill using modern LWD and MWD systems, way past the current limits of 150 or 175 degrees Celsius. Insulated drill pipe keeps the drilling fluid cool until it hits the drill bit. It actually hits the formation and shocks it, which speeds up drilling speeds, but also it keeps the bit and the electronics cool. So you can drill all the way down to 350 degrees Celsius using this insulated drill pipe. We're continuing to develop it so that it works and works better and has fewer issues as you drill your well. For magnetic ranging, that was touched on in the previous two presentations ago. We've developed a better way to do this so that you can magnetic range and drill at the same time. So these are all patented. Some of them are available. If somebody wants to use insulated drill pipe for a different project, we'd be more than happy to license out the technology or even lease a string out to you. Similar for magnetic ranging. Now, other things, the ABCUS dispatchability control algorithm. I'll talk about this in a few minutes, but what we try and do is we can control an Everloop's output to follow any ups and downs in the local grid, and then we develop and test it out, control algorithm to make sure that we can follow rapidly and rigorously what is happening in the local grid. And this is very attractive from a power utility point of view because we can offset solar or wind in a very efficient manner. For organic Rankine cycle engines, we're actually using a Mitsubishi Heavy Industries or their subsidiary ORSA unit in our installation in Garrett Street in Germany. We're looking at certain new technology with them, but that's mostly their technology rather than ours. And then we're putting everything together into a package so that we can simulate potential projects or actual projects prior to drilling. I'm not going to go over this slide. I'm just going to say that we are different than other geothermal systems. some people would say they might have certain questions about these, but I'll let you look at these later. These should be available after the seminar is finished. I would like to go into this slide a little bit though. From an environmental impact point of view, Everloops are very beneficial. In the bottom right-hand side, you see here that we have a very small footprint, and this was dealt with a few presentations ago. The small size of an Everloop and our ability to site ourselves with no fracking, near a city or even in a city, means that you can actually put an Everloop exactly where the load is, where the heat loads are or where the electric loads are. So you don't have to deal with the transmission costs of electricity or the transmission costs of heat. Looking up on the upper left-hand side, there's very little greenhouse gas emissions. Once you finish drilling it, during the operation phase, there should be absolutely no emissions. Unlike conventional geothermal, where the well might be burping CO2 or other gases, greenhouse gases, during operations. If you look on the upper right-hand side, this is actually very interesting, especially nowadays. We don't use a lot of rare earth elements, and the supply chains for oil rigs, for drilling rigs, is actually mostly contained right now in North America, in Australia, in Europe. In order to drill Everloops, all you need is basically iron and people. Unlike solar or wind, where the supply chain is controlled heavily by certain countries, which are currently trying to control the supply chains a little bit more strictly than they did in the past years. We don't use water during the operation phase. We have to tap it up a little bit, but unlike EGS, where there's massive losses during the operation phases, we use very little new water. So we're very attractive for areas where water usage can be problematic. So these are special things about Everloop that are perhaps different than other solutions available. I spoke a few minutes ago about dispatchability. Now, an Everloop there's no production from the formation, so there's no changes in pressure or temperature that could cause depositions and problems with scaling and things like that. You can control an Everloop 100%. You can shut it in, you can open it up wide. So what this means is that you can follow the solar load or the wind load during the day. You can shut your Everloop in during the day when you've got lots of solar coming up. You can let the heat build up in the formation, and then you can release it suddenly to handle these humps that you see during the early morning or early evening. Because this is what is difficult for a utility to handle, and we provide almost a perfect solution for them. Not enough to actually tune the grid. It takes minutes, not seconds, for us to spin our Everloop up, but it's extremely attractive from an electric utility point of view. And one of our biggest partners is indeed an electrical utility. Now, at the surface, we want to either provide heat or power to our customers. And that's just a very basic organic Rankine cycle work engine. There's any number of manufacturers in the world, in Europe, in the United States, in Israel, in China. So this is very much off-the-shelf technology. What is good, though, is when you can share the load and not only provide heat to the local network or to an offtake heat client, but if you can provide electricity too, because you can then balance those two loads to find the most economical solution for a particular area. And indeed, that's what we're doing in our first commercial project. It's set up for electricity, but it's also, we're going to be providing to the local heat network as well. And of course, you know, if you can provide directly to a heat network and sell that heat, it's actually more economic to do that than to change it to electricity and then put it onto the grid and then either use the electricity for heat or for other services that way. This is the most exciting part, though. This is our first commercial project. Drilling is underway. This slide is a little bit old. We've actually completed drilling for the first of the 4 Everloops. Learned a lot on the way, and we're actually just getting ready for it to set up for first power, definitely this year, hopefully a little bit earlier than that. If you want to come out and take a look at this, we do have a visitor center, and we do welcome partners, government, potential partners, academics. Oh, there we go. Now this project itself, you can see in the background how environmentally benign we are. In the background there, it looks like you've got farmers' fields, you've got restaurants, hotels. The nearest town is, you know, a really good golf drive away, or maybe 3 or 4 golf drives away. We got permission from the locals. We explained about what we're going to do and how we're going to do it, and we received a substantial amount of support from the local governments. Indeed, they're setting up to build a heat network to become an offtake customer for this project. Now, it's actually, the project itself is pretty big. These drilling rigs A and B over here, they're pretty substantial. I believe they're in the £1 million range. And there's not a lot of heavy-duty rigs like that just kicking around. You know, you need to really make these Everloops economic. You need more than a 3,000 meter depth or 4,000 meter depth. The Garrett Strait project is going down to about 4,500 meters, and then the laterals kick off, and they're planned for 3,000. But as it turns out, the torque drag is less than we thought, so we'll be extending them a little bit farther out. You can see the air coolers are there. When the project is finished, the rigs will disappear. The ancillary equipment and the water tanks, the rock pipe tanks that you see in front of rig B, they'll disappear. And then all you'll have left will be the visitor center, the office, the generator, and the air coolers. And the substation and whatnot. It's a very complicated project. We're learning a tremendous amount by building it, and we'll be able to take these learnings and then roll them out to other projects in the rest of the world. The other projects could be projects that we are leading, or if somebody wants to license our technology, we're more than happy to help people build their own Everloops. In the future, we intend not to be an infrastructure company, but a technology company who continues to develop their technology and then let other people use it. So that's really our future right there. It's not building 1 or 2 or 3 more projects and then 5 or 6 or 10. It's building a few more projects and then just licensing our technology and letting other people build them in Australia, in New Zealand, in Japan, Singapore, France, wherever they have the need for heat and for electricity. That's it from me for right now. If you have questions, please do share them. Thank you.
Thank you very much for a fascinating presentation. Do we have questions? Online, in person? We can probably fit in a couple.
The first question is from Laureano Gonzalez, and the question is, how do you avoid collapse of the open hole section of the loop?
Okay, good. During the drilling process, we just use regular mud and or water, and the hydrostatic pressure keeps it stable, or should keep it stable. That's very traditional oil and gas technology, very well known. During the production phase, we keep water in the loop, and it's the water that flows through to pull the heat out, and that hydrostatic pressure will continue to hold the walls back. In addition, when we use rock pipe, that actually seals off the wellbore. It destroys all permeability, so you won't have any kind of fluid coming in from the formation, and you shouldn't have any formation or any fluid going out to the formation. So there's actually no delta. If you look at the stability equations, there's a delta P that happens across the wellbore, across the wellbore face, the wall, and that doesn't occur because we're not trying to produce fluids from the formation. Is that a good answer? Does that satisfy you?
I think that's good. That's not my question, but I think that's good. Other question we have is, what are the minimum technical requirements you're considering to start a project? You mentioned the site of the Gare Street project, but what is the range of cost for, say, a 1 megawatt project averages at?
Well, I'm not going to give you costs because that depends on local availability of rigs and whatnot. The most important thing is that the more data that you have available for an area, offset wells, cores, logs, seismic, the easier it is to make a good evaluation of a particular opportunity. If there is offtake, either heat offtake or electric offtake, that enables you to then calculate the revenue side of the equation. And between the two of them, between the cost of drilling and the revenue, you can determine if the project's going to be economical or not. If there's places where the regulatory regime is behind or uncertain, then that would be a negative. But we can actually take a quick look at an area for a very minimal cost and then determine how attractive it is. We've actually developed some software as well that can do the same thing. It's still not 100% click and proceed, but it's getting there. And that software will be available to people who want to lease it.
In the room question, we can get a microphone up the back. We're just getting a mic to, here we go.
Thanks very much, James. That was a really interesting talk. I'm wondering, what is the ideal geology that you're targeting? Are you looking for deep sedimentary type systems, or are you looking for those granites for that extra heat? What works out to be economically preferable?
A lot of the projects, great question. A lot of the projects that we're looking at today, because of the the cost of drilling, unless it's an extremely hot sedimentary basin, we're trying to focus on what we call our 2.0 technology, which is granites. There's radiogenic contributions from radiogenics that keep the granite hotter than just the background geothermal gradient, and that becomes very attractive. In addition, a large stable granite body, even though it's hard to drill initially, the idea is that you learn how to design a bit or a drilling program to drill that fast. And we proved in our Eavor Deep, we, typically people would say, oh, you can only drill granite at 2 meters an hour or 5 meters an hour, or, that's what you expect. But we showed that we could get much higher drilling rates, 20, 25, even higher, by very carefully designing bits for the rock that was there. We did have problems there when you had, for example, a hard granite interleavened with a chert zone, because you could drill a bit you can design a bit to drill the granite fast, but we couldn't design a bit that could drill granite fast and then not crash out when it hit the chert. So, very, very stable, very large, isotropic, unchanging granite would be the hot granite would be the ideal geological zone.
Okay, we should probably wrap it up there and thank James again very much for the presentation.
Okay, thank you.
Great. Our next speaker is someone who needs no introduction to many of us. He's messaged me to say, could I please introduce him as Roland from Stanford? I couldn't say no to that. So our next speaker, Roland Horne.
All right, thank you. Thank you very much, Rosalind. So I am going to talk to you here about EGS. You've heard it mentioned several times. And in particular, I'd like to draw your attention to some of the new things that have happened since 2014. And the reason I chose that particular date is that in 2013 and 2014, ARENA there in Australia empaneled a group to look at geothermal in general, actually, in Australia. But a lot of the focus was actually on EGS, and that's going to be my focus here today. Talk about a little bit about what was concluded in 2014 and what's happened since. Now let's talk about EGS. You've seen plenty of pictures about it, so I won't need to spend a lot of time. The general idea is that in places that are not blessed, like Nigeria and Philippines and Indonesia, where you don't have permeability to create a geothermal system, you make your own by fracturing, essentially from well to well. And this particular cartoon shows the classic idea of EGS with vertical or somewhat deviated wells. Come back to that in a little while. And if we look at the United States, which of course is where I am currently, if we look at a map of the lower 48, this is a map that we created at Stanford based upon 500,000 well data from oil and gas wells largely. At 7 kilometers depth, which is drillable depths, as you've been hearing all day, if we look for 140 degrees, which is that straw yellow color, that's kind of the temperature that works for binary plants. You can see certainly there are areas where red and orange, which of course are more attractive, but with the straw yellow, we can kind of do that over much of the lower 48. The big question, of course, is at what cost? And that's something I'll come to a little bit later on. So EGS as an idea has been around for 50 years. It was invented in Los Alamos in the 1970s. And there's a number of issues that people have been struggling over time. About 15 or 16 full-scale EGS projects have been attempted. And these are the problems that they've been addressing. In order to have EGS to work properly, or for that matter, any geothermal system to work properly, you have to get in contact with large volumes of rock, and I'm talking about cubic kilometers of rock. So it's all a question of surface area to volume ratio. You need to have a distribution of fractures, you need to flow through all of them and get your fluid out to the heat that's in the rock in order to recover it. The third issue that you see on this slide is having sufficient flow rates. This is actually a point which is often lost on our colleagues from oil and gas, is that a geothermal well, given the financial value of a barrel of hot water is about 50th of that of a barrel of oil. The only way you can make money with geothermal energy is to produce massive amounts of fluid. So a normal commercial geothermal well produces about 80 kilograms per second, which is around 50,000 barrels a day. That's a lot. And that's why geothermal wells are drilled to such large diameters. And then finally, you've also heard again today about induced seismicity, not necessarily a technical issue, but it's certainly one of a public relations barrier, because any seismicity that causes public concern is basically the loss of social license to operate. Now, coming to the first issue about flow rate, this is a typical conventional geothermal well from my collection. You see this particular one is producing around 70 kilograms per second. So people are making money with that. But if we start looking at some of the earlier attempts at EGS, you can see that it wasn't quite as good. So this is an example from the project in Source in France in 2005. And you can see this well was producing 8 kilograms per second. Here's another example from Japan. They had 2 EGS projects there. And once again, if you look at the pink line, it was producing at about 8 kilograms per second. Now, over time, people started to get a bit better at doing this. The first commercial EGS project in the world, which is in Germany, in the Rheingraben, got up to 70 kilograms per second. It's a bit of controversy about whether this is really EGS, because actually only one of the wells was stimulated. So it's kind of a hybrid between a conventional and an enhanced geothermal system. So there are actually 5 projects, EGS projects in the Rheingraben, 2 in France and 3 in Germany. 4 of them currently operating. And what you can see here, I draw your attention to the size of these projects. 3 megawatts, 1.5 megawatts, 4.5 megawatts. Rittershofen, the one at the end, is actually not an electrical producer. They provide industrial heat to a factory, 24 megawatts thermal. So were they to produce electricity with that, it would be 2.5, 3 megawatts. So these are operating commercial plants, but they're not very big. That's the point. And then we come to Australia, and actually there was, of course, also an operating EGS project in Cooper Basin in 2013. They produced 1 megawatt for a relatively short period of time. But of importance to note here is that if you look at the sequence of experiences, they went from 20 kilograms to 30 kilograms per second, and ultimately Habanera 4 produced 35 kilograms per second, which is not 70, but it's sort of in spitting distance. They were halfway there. So over time, people got better at doing this. Now, coming back to the ARENA report that was written at the end of the study in 2014, I picked out some of the key points. And what you can see here, this number 7, you don't have to read all of that, but what number 7 is about is basically all of the issues that I just discussed in trying to get sufficient flow rate. Number 8, 9, and 10, one is about raising money, but basically they all point to drilling costs. And that's a significant part of the story of what I have to say today. And here's a table from that ARENA report. And you can see under a number of different scenarios, basically the conclusion was that the likely cost, levelized cost of electricity, LCOE, was $200 per megawatt hour or more, which is basically not competitive. So coming back to the United States, there have been a number of EGS projects here, starting with the first one in Fenton Hill in the 1970s. But there are currently 4 active projects taking place at the moment. And right there up at the top, Blue Mountain, you will notice this is a commercially operating plant right now. It's been running since October 2023, which is producing, importantly, 63 kilograms per second. So they're up in that area that we need to make money, and they're providing that flow to actually an existing geothermal plant at Blue Mountain, which is generating 3.4 megawatts from that flow. And then we have 3 others there that I'm going to talk about 2 of them. So I'd like to talk about my university, Stanford University. This handsome group is our students and staff in 2016. And I draw your attention to this gentleman in the middle. His name is Jack Norbeck. And this is another picture of Jack Norbeck. He and another of his Stanford colleagues, graduating at about the same time, co-founded a company called Fervo Energy, which if you haven't heard of, you certainly will. And what they decided to do was, rather courageously, create their own EGS company, more or less straight out of graduation. And importantly, this principal message I have to give today is that what they did changes everything that you ever thought about EGS. Because instead of drilling vertical or near vertical wells, what they chose to do was to adapt the technology from oil and gas that's used widely now in the US and other places for shale developments, drilling horizontal wells, fully completing them from top to bottom using gun perforation and multi-stage fracturing, and also using propped fractures, all three of which were kind of novelties in geothermal. And that first project that I pointed out to you, which they called Project Red, which was on the boundaries of the Blue Mountain field, they drilled the first horizontal wells ever in geothermal, did a multi-stage fracturing, and put them, as I mentioned, into operation. And what you can see here, the plug and perf technique that they used, they had 16 stages in one well and 20 in the other. And again, importantly, making use of proppant. And that was kind of considered to be a bit daft at the time, because a lot of EGS projects had assumed that EGS stimulations in hard rock like granite would be self-propping and would not need to use proppants. There have been cases where proppants have been used before in other projects, but it wasn't widely considered to be a good idea. But what you can see, the experience from Project Red, is that in the 16 stages of their injection well, they had a pretty good distribution of flow in all of the stages, not completely uniform, but all of the stages were active. And let me remind you the point I made 10 minutes ago, which was that achieving distribution of flow across large volumes of rock is what EGS requires to be successful. And that project, as I say, went into commercial operation October 23, and now is still in operation today. So then Fervo moved on to a full-scale project in southern Utah, where you can see here they basically started marching across the countryside with making these horizontal wells. And their strategy is to drill 8 wells per pad and put 1 power plant on each pad, and they're just going to replicate that across the countryside. And this is one of my favorite geological cross-sections, because it actually shows 3 separate geothermal projects. So Fervo, as I mentioned, is there on the left. In the middle is Forge, which is the US Department of Energy's research project on EGS. It's a slightly different strategy. You see the wells are inclined at 65 degrees. There's no intention there to make electricity. The idea is to test ideas and tools and equipment and modeling methods, etc. And then over here on the right is the Blundell conventional geothermal plant, which has been in operation since 1983. And if you look at those red dashed lines, the isotherms, what you can see is that they rise close to the surface at Blundell. And that's because it's a convective system with fluids flowing upwards through major faults. And in contrast, in Forge and Fervo, all of the isotherms are flat. It's a purely conductive region, doesn't have major faults and fractures, which you don't want in an EGS system because it takes the fractures out of your control. And they're developing in a purely conductive environment. And looking at that same picture and on, you can see the strategy that Fervo is following. It's actually in 3 dimensions, and those horizontal wells are drilled, in fact, at different levels, which they call benches, different depths. So they're already been stimulating over there. They're using about 30 stages per well. And last year they did a flow test on their first pad. And what you can see here, they got up as high as 120 kilograms per second, leveling out at around 90 kilograms per second, which they estimated at their producing temperature of around 200 degrees would be able to generate 9.5 megawatts per well pair. Now, one of the important things, again, let's come back to drilling costs. If we look at the drilling experience originally in the old Blue Mountain and the conventional wells that they drilled, you can see here pretty typical experiences for geothermal drilling, anywhere from 40 to 60 days, just drilling down to 2,000 meters. Fervo came along and alongside, neighboring that field, they drilled much deeper, including the horizontals, in about the same time, although on the kind of the faster side. And then as they learned, moving ahead with their experience, they got faster and faster in their drilling in Utah. That's what they call Project Cape. And they have now drilled actually 20 horizontal wells in total. And the most recent one, which they completed about 2-3 weeks ago, they drilled in 16 days to total depth. And that is a completely staggering experience for any kind of geothermal drilling. And this shows the learning curve that they experienced. This is actually from about a year ago in terms of the length of time it took them to drill their wells. So how they did that actually is quite significant too. Forge had a very similar experience. Forge also had very rapid drilling experience. They had careful optimization, day-by-day optimization of the drilling methodology, adopted and adjusted as they went. But importantly also too, they used PDC, polycrystalline diamond compact bits, which have been around for decades. Actually, they were used in Fenton Hill in the 70s, but are generally considered by most geothermal drillers to be too expensive. Well, that turned out not to be the case, because both Forge and Fervo found that they could drill much faster with PDC bits by putting more weight on bit than they could normally sustain with a roller cone bit. And also they had much longer bit runs. They had some cases where they drilled as long as 2,000 meters in a single run. So that saved them a lot of time, and it saved them, of course, a lot of money, because if you halve the length of time to drill the well, roughly speaking, you also halve the cost. So accompanying the map I showed you earlier of temperature, the studies that we've done at Stanford looked at levelized cost of electricity by this gentleman here at the bottom, Mohammed Al-Gibran. And the average cost of electricity in the United States is $70 per megawatt hour that you see marked there, which is kind of the orangey red. So there's certainly places around there that are orange and red that would be places you could make money with EGS systems, but also a lot of blues and greens where you could not. This, however, was in 2022. That's before Fervo or Forge drilled any of their wells. If we take their experience into account, where they halved the drilling time, in fact, sometimes they reduced it by 70%, this is what the picture looks like. So again, it's a slightly different scale, but I've marked $70 per megawatt hour, which is the straw yellow again. And what you can see is that the large majority of the United States could make money with EGS at a competitive price of $70 per megawatt hour. So then in the hurdles of the technological hurdles that I mentioned have all basically been met in those two projects, Forge and Fervo. And I didn't mention induced seismicity, but in fact, they did not have problems in either project with that. And one of the reasons why is that succession multi-stage fracturing were making many but smaller fractures than earlier EGS projects had. Single vertical wells with massive hydraulic fractures, which ultimately led to greater seismicity. And then importantly, they substantially improved their drilling rate. And as you see in this picture on the right, this is a picture I took in June. They currently have 3 33 megawatt power plants under construction in Project Cape, the first of which will start operation in January of 2026, and the other 2 by the end of 2026. And they have power purchase agreements for another 400 megawatts of production in the same project by 2029. So we're not anymore talking about 3 megawatts, 4 megawatts, etc. We're talking about sufficient magnitudes of projects which compete with fossil fuel. So coming back to ARENA's 2014 report, there was some clever alliteration there in terms of decisions what to do: resume, reconsider, or reboot. Reconsider, I think, is a euphemism for give up, which I think seems to have been what the choice was. But entering back to these same 4 points, the fact that we now have the ability to get the enhanced flow rates that both Forge and Fervo showed actually opens up a much wider range of possible settings in which you could do this. It's still an issue to raise capital anywhere. But what you will see then in Fervo are 2 Stanford graduating students in their early 30s who started a company with the 2 of them in 2017 and raised more than $1 billion. And are on track to actually be producing 500 megawatts within the next 5 years, and 100 megawatts currently under construction, largely as a function of reducing costs. And I showed you drilling, but that wasn't the whole story. I don't have time for the rest. So let me show you this map. You saw an example of this earlier, I think, from Jay Egg in terms of heat pumps. This is for EGS. So this is a government report. So they're talking here about first of a kind, FOAK. I don't know if you use that expression in Australia. So they're the government. They don't say what this was, but this, in fact, was Project Red. And then over here, basically, is Project Cape. So these are not speculative numbers. These are numbers that have actually been achieved. And Earthshot is what the DOE calls it, is to go further than that by 2035, as you see. So once again, remember, $70 per megawatt hour is the current average cost. And comparing that to what it was in 2014, at least in Australia, there's a much wider open door than there was at that time in terms of price. So with that, I will stop and thank you very much for your attention.
Thank you very much, Roland. Are there questions? In person.
Thank you, Dr. Horne. Appreciate the presentation. This is Hans Dick with SLP. Do you have any insights, I guess, at least publicly, on how at least the pilot in Nevada has been performing in terms of temperature declination or water loss, or in terms of the fractures, if they're changing over time, which I guess it's more looking at the production, I guess, sustainability of EGS over long periods of time?
I don't have any information to give on that, just because I don't know it. It is still in operation. That plant had the plant itself to which they were supplying had some issues that they shut down for a while, but they're back in operation now. Circ, who operated it, recently sold the plant to Ormat, but it's still in operation. The issue about water loss is actually an interesting one to talk about. One of the things that, one of the strategies that Fervo is currently following, and that's the same in many other projects too, is to basically pump water into the injectors and take whatever comes out of the producing wells. And the consequence of doing that is it takes some time to basically put the collective network, the reservoir, into a different pressure state, during which time actually they lose fluid, as has been pointed out by others. But once the reservoir goes into equilibrium, basically their water loss falls off. It doesn't go away, but it becomes a lot smaller than it is to start with. And furthermore, there's another possible strategy, which they're not currently using, but they may in the future, or in either that or other projects, which is to pump the producing wells. So the strategy there, instead of pushing the water through, you basically pull it through. You pump the production wells for whatever amount of there is no water loss.
Okay. Yep. Sorry, your camera was just wavering, but we can see you again now.
It wasn't me. It was somebody there pressing the button.
Any other questions for Roland? Yes.
Thanks for your talk. That was very interesting. Is this geologically constrained? Like, can it apply anywhere in the world or in Australia, or is it constrained by geology in the States?
It's certainly influenced by geology. There are certain places that would be very advantageous for EGS of the type that I showed you. And of course, these sites that you looked at were carefully chosen. And it's no accident that Fervo is right next door to Forge and that Forge is right next door to Blundell, because both of those subsequent projects actually made use of the geological understanding kind of lower the risk of the projects that they undertook. And they chose on purpose to drill into those granite bodies with the intention of taking advantage of that particular geology. What they gained, let me sort of tell you, that the advantage of that particular geology that they're working in there is that there are not many natural fractures. So one of the reasons that geothermal drilling is so challenging is of lost circulation. You drill into a natural fracture, you lose full circulation, it's difficult to get well control. You spend a lot of time, you may twist off, and that's what costs money. Drilling into granite like they did, both Forge and Fervo basically drilled with full circulation throughout their whole drilling program. They could straightforwardly, I won't say easily, but straightforwardly complete the wells top to bottom. And that's what allowed them to actually drill as fast as they did. There are other places that would be less suitable. If you had a formation that was kind of broken up or very complex, that would be more difficult. But if you had, that doesn't seem to me any particular reason not to imagine trying it. But a very contiguous, homogeneous body of rock would be your number one choice for an EGS system. Sedimentary formations are going to be more problematic because, the issue of the fracture closure. But once again, having pioneered the concept of using proppants in EGS systems, fractures have been made in the millions in the shale plays of the United States. So keeping a prop fracture open in a sedimentary formation is not a big deal. So there's no reason why you couldn't, in principle, do the same thing in sedimentary formations. And of course, Australia's got plenty of granites too, where you could do that.
Thanks, that's a great answer.
Any other questions for Roland? Anything online?
There's one online question from Andrew Wank, and I think you sort of answered that in your closing remark there. But his question is, are you aware of any granite type geological setting in Australia suitable for the Fervo type approach?
The short answer to that is no, but I'm sure they're there. I'll leave that to Australians to find. And it doesn't have to be granite, it just has to be contiguous. Mm-hmm. And it doesn't have to be contiguous, it's just that what you'd like to have first.
Mm-hmm. Okay, well, I think that wraps up the questions for Roland. Thank you very much for joining us. Always fun to hear where Fervo are at. Right, so that leaves it to hand back to Graeme to close out the day and to think about where to next.
Thank you, Roz. I'll take my lead from Roland and speak quickly, because we should have been into the beers about 50 minutes ago now. But before I launch into my slides, as we will all be rushing off to the bar straight from here, I will just do a shout out to somebody who's not here, but has been critical to getting today to be the success that I think it has been, and that's Jess over in New Zealand. I know you've been online all day, Jess. We have 5 board members on the Australian Geothermal Association. The president speaks with an American accent. Martin speaks with a French accent. Roz speaks Kiwi. Our treasurer speaks with a Dutch accent. I was born in Melbourne. I'm an Australian. But Jess, who actually did a lot of the hard work for today, not only speaks with a Kiwi accent, but still lives in Kiwi land. So she's been helping out from across the ditch. So thank you very much, Jess. I wish you could have been here. And without further ado, I will give a vision of sorts for Australia and talk about the topic of how we get there. Maybe not give answers. Mark, when he started the day, he spoke about what you will be hearing about. We've had 12 speakers between Mark and me who have told you amazing details about a lot of very interesting stuff that's been happening over the past decade. I'm going to wrap up by telling you again what they've just said, and then sort of a bit of thoughts about what it all means. So at the start of the day, we heard Marit and Rebecca explain that geothermal energy provides extensive benefits, that the world is accelerating development of geothermal energy projects, and that governments play an essential role in supporting the growth of new geothermal industries. Ros recounted how Australia has an ongoing history of small-scale geothermal projects, a lot of them for heat, often led by local governments, and that externalities largely halted attempts at larger-scale geothermal development in the early 2010s. The four gentlemen, Jackson, Jay, Hans and Jeremy, collectively highlighted the potential for mature and emerging technologies to deliver huge amounts of geothermal energy to optimise Australia's energy transition. Amanda presented strategies to meet the challenge of financing a new geothermal industry to the point of self-sustainability, and nobody wants to have subsidies forever. We just want to build a self-sustaining industry in geothermal in Australia. Sam and Kifayat gave a snapshot of improvements in subsurface imaging, drilling and production technologies over the past decade. James described the emerging commercialisation of deep closed-loop geothermal systems, especially for industrial heat, which is where I think the real opportunity in Australia for those sorts of systems are. And we've just heard Roland report that EGS is now considered a commercial technology in the US, with developments of hundreds of megawatts underway as we speak. So that leaves me to wrap up the day. And actually, no, this is the sort of the last point, that some of the key findings from ARENA's IGEG report in 2014, as we've just heard from Roland, are now demonstrably outdated. And I asked an AI image generator, please make me an image about a demonstrably outdated 2014 IGEG report from ARENA, and it came up with that snapshot on the right. So the vision for Australia: we should all be nuclear families with dogs and go hiking in the mountains. But from a geothermal perspective, here's just some things that perhaps we should and could shoot for in the geothermal sector in Australia. Maybe large-scale adoption of ground source heat pump to minimise the electricity demand peaks and actually reduce how much extra transmission lines and power plants we need going forward. And we heard from Jay the really significant benefits that ground source heat pumps can play in that space. How about we extensively and widely utilise the warm aquifers that we know underlie huge parts of Australia. The Great Artesian Basin, just on its own, covers 1/7 of the continent. And granted, there are not that many people out there to be using the warm aquifers, but there are many others. And Ros put up a map showing where the sedimentary aquifers are with known warm aquifers, and they're not all out in the unpopulated parts of the country. There are many very close to populated zones. Jay showed how thermal energy networks actually distributing heat from between prosumer and prosumer, so you can be a heat consumer one day and a heat producer the next day, and share heat with your neighbours and draw heat out from the earth and share it around. We could do that here. Utility scale electricity and or high-grade industrial heat being produced from hot sedimentary aquifers using the technologies that we heard about from Halliburton and SLB and Mark's land down in the Otway Basin and Mark's land down in the South Perth Basin. You've got to be a Mark to have a hot sedimentary aquifer. Industrial heat produced from closed-loop geothermal systems, an Eavor type system. We have some very large-scale industrial heat users, as Keith in the audience could tell us all about. And how about our own hundreds of megawatts of large-scale EGS systems out in the less populated areas where people are talking about large-scale wind farms and large-scale solar farms? We could have the same scale of EGS, but using about a 10% of the footprint. So there's some elements of the vision. The heat has always been there. A lot of the technology has really always been there, although it's been improving over the past decade a lot. But we don't currently have a geothermal power plant in Australia. And while we do have low-grade geothermal heat developments, they're sort of stepwise and small and localized and run by local governments or small industries. Why aren't we at scale? So one of my hats that I wear at the IGA and in Geneva sometimes is I'm a member of the United Nations Expert Group for Resource Management, coming from the geothermal side of things. And I'm not going to proselytize about UNFC and the UN system, but there's a series of documents that is the United Nations Resource Management System, and under that sits the United Nations Framework Classification for Resources, and under that sits the UNFC geothermal specifications. It's like a big reporting code. So I'm not here to proselytize about the UNFC today, but as well as a reporting code like a JORC code or the old Australian Geothermal Reporting Code or the SPE code for reporting petroleum resources, the UNFC provides a framework for really assessing a whole of project, sort of a 30,000 feet view down on a project and work out what stage of maturity is this project at, not from a technical, or not only from a technical perspective, but also from all those other things that have to align to get a project off the ground. And we've been hearing a lot about all those other things today. And we'll just give a shout out to the Government of Queensland, which was the first jurisdiction in the world to mandate the use of the UNFC for geothermal resource reporting. So UNFC, it provides a framework for thinking about a project and then classifying that project in terms of, is it just a prospective project? Is it a non-viable project? Is it a potentially viable project? Is it a viable project? So, but to get to that point of assessing a project, you really need to look holistically at the project. So I'm not, as I say, I'm not here to go into the fine detail. Literally run courses for 3 to 5 days to explain all this because it's confusing. But there are two axes, an E-axis and an F-axis, and the E-axis is really the one I'm going to focus on here because that sets out like 10 or 12 different non-geological and non-technical elements that really all have to fall together for a geothermal project of any kind. This could be a ground source heat pump for your house up to a 500 megawatt EGS power project, but any geothermal project has to be able to tick off all these boxes or it's just not going to happen. And on the F-axis, that's the more technical kind of things. How much geology's been known? Has it been drilled yet? And has a power plant been built? So there's the two axes, but looking mainly at the E-axis, and what we're really aiming to do is move up the maturity scale on both axes. So move forward on the eco, social, finance E-axis, and also move forward on the technical axis, doing the science and engineering. And as we move forward on both those axes, we move up towards the green boxes, the viable projects, the actual energy generation, and start making money. So I thought, right, we don't have a lot of big projects in Australia, so let's use that UNFC framework and just do a critical assessment of a few projects that I'm very familiar with, and just see how they rate on largely on the E-axis side of the UNFC assessment framework. So this is the Smart Geothermal Industrial Loop that I've been working on with Rachel, supported by the Victorian Government, and other people in the room have also played a role, Martin in particular, who's left the room, so he's not in the room. But Morwell in the Latrobe Valley, about 2 hours east of Melbourne, is the Latrobe City Council is building a new logistics centre, and it's underlain by a known hot aquifer. Oh, he's in the room. Hi, Martin. And thought, well, can we do a distributed geothermal heating network for this new logistics centre so that every new tenant in that logistics centre can draw on the geothermal energy just from a single production bore and reject the water into a single injection bore. So, we call it the Smart Geothermal Industrial Loop. So we've got support from Regional Development Victoria and Latrobe City Council, and working with some very talented engineers in the university and some very talented hydrogeologists sitting in the front row. And we've designed from a technical perspective what such a system would look like, how deep the bores would be. We've got a good handle on how much the bores would cost, how they would have to be designed. We've got a good handle on what the temperature of the water will be, how well the water will flow, how we would set up the piping and the pumping networks, and where the heat exchangers and heat pumps would need to be, and how much electricity they would use. We've got the whole system modelled to an inch of its life, but it's not built yet. We haven't drilled a hole yet, and nobody's sort of stepping forward to drill that hole. So what is holding it up? So looking down the E-axis things, the environmental, social, economic, market access, land access, legal, regulatory, political, governance, external approvals, I sort of ranked where we are, where this project is on all of them, and some things rank good. Good is on the left, not so good is on the right. And there are three points that sort of stand out. There's market access, because this is a proposed logistics centre. There are no tenants yet. There's nobody to use the heat. And are we going to drill and build one of these systems when there's nobody guaranteed to actually use the heat? So that's a bit of a barrier at the moment. Legal gets a bit of a mark down because there's no legal structure in Victoria for buying and selling heat. So there's a whole sort of market structure uncertainty there. And governance. We don't know yet who would actually own and operate this system if it was built. So there's those 3 points, which are non-geological, non-technical, not engineering at all, but there are 3 points that are very definitely stopping this thing from going ahead at the moment. So to move that project forward, we really have to address those 3 points, and that's sort of a big part of our research at the moment with the state government is, as a geologist, how do I improve finding tenants to go and use the heat? As a geologist, how do I help improve and develop a legal framework for buying and selling heat in Victoria? And moving ahead to the next example. So when you rank this on the UNFC framework, it comes up as a prospective project. So it's not dead, it's prospective, but there's some serious challenges that we're addressing to try and get this thing moving forward. So we saw the GeoMap prediction earlier today that Victoria, if you actually drill into GeoMap, Jackson didn't put this number up on the screen specifically, but the predicted potential for geothermal power in Victoria at present is 12 gigawatts of geothermal power, according to the recently published potential map from GeoMap. So that 12 gigawatts, let's go build it. Hey, what could possibly stop us? Legal stuff and political stuff is what could possibly stop us in Victoria. And probably a bit of social and economic and land access and maybe some regulatory problems as well. But the key barriers that really rank way on the lower bad end of the E-axis spectrum in terms of UNFC are legal and political in Victoria, largely because we have a Geothermal Energy Resources Act 2007 in Victoria, which only grants a new geothermal energy licence by tender. And when do you think the last tender process was? It was 2007. So since 2007, Mark is still tenaciously clinging onto a licence that a prior company was lucky enough to get, but that really is the only licence to do anything geothermal in Victoria in terms of power generation. And the only thing that's going to change that and allow other companies to come in and try and pursue some power generation projects into Victoria is if the political leadership decides to pull the trigger on another tender round when the last one was 18 years ago. So that's basically dead in the water at the moment, apart from the Koroit project in Victoria. So Victoria is not prospective for geothermal power right now, not from technical viewpoint, but from political and legal viewpoint. According to UNFC, the UN framework, Victoria is not prospective. What about large-scale rolling out ground source heat pumps across the country? Go through the same process and we find economic uncertainty and regulatory uncertainty. That they are prospective. You've heard about one of the world's largest ground source heat pump systems has just been installed in the War Memorial here in Canberra. And there are increasing numbers being installed just in domestic properties and commercial properties around the country, but each one is individually assessed and sort of considered back and forward. And a big part of the reason that is, and what's stopping a really large-scale rollout, is regulatory affecting the economic cost benefits of ground source heat pumps. And the key point here is that ground source heat pumps across Australia are ineligible for the same subsidies and benefits that are given to like solar heating systems and air source heating systems. Geothermal systems are ineligible for those subsidies. So this one in the UN system, large-scale rollout of ground source heat pumps, sort of sits in the development unclarified, which sort of means it's a project-by-project assessment. Things slow down. It's a case-by-case assessment of if it makes sense in a particular location for a particular end use. So because ground source heat pumps are ineligible for rebates that are readily available for other systems for producing like hot water. So that's just 3 case studies that I'm familiar with. Do a quick straw poll around the country, as we did as the AGA board, and we came up with like a laundry basket of other obstacles that are stopping projects happening around the country. So new licences are only attainable by tender, not just in Victoria, but Western Australia, and I believe some other states, Queensland, I think. There's uncertainty over whether fracking will or will not be banned for EGS, and on one case, again speaking from my own home state of Victoria, we have the Geothermal Energy Act and we have the Victorian Gas Act. Fracking is banned under the Gas Act, but Mark had to sign a contract saying he would not frack either, even though he's operating under the Geothermal Act, and the fracking ban is not in the Geothermal Act, but Mark is being forced to not frack anyway. So hopefully you don't have to, and Schlumberger can help you out there and map out where all your fractures are going to be. Failure of states to award new tenements in a timely manner. Ros put up that great tenement map showing like large parts of the country under offer, but some of those offers have been in place now for 2 or 3 years and then they have not yet been awarded. So that falls down to the state regulators. For low enthalpy, just hot water projects, there are complex regulations around the reinjection of the cooled water once you draw out the heat. So in Victoria, for example, you need 4 separate licenses just to do a small geothermal doublet, and that stops a lot of projects cold in their tracks, just the paperwork involved. Very small, vanishingly small number of powerful drill rigs of the sort that James showed are required for a large-scale Eavor type project. So we can't just immediately start developing large-scale geothermal projects. We would have to build up a bit of a drilling rig fleet in the country. Individual projects lack scale to justify politicians and regulators making changes to acts and regulations. One small project having difficulties is not going to be enough to change a regulation or change an act. Even 6 projects is probably not going to be enough. So at what point how many projects is enough to change acts and regulations? Well, I would argue just one minister would be enough to change an act or a regulation if the choice was made. And the skilled workforce in geothermal in the country is in this room, really. So, but if you bubble all this down, ask why 5 times, and you get to the ultimate answer. And there is little political awareness or interest in geothermal energy at this point in Australia. And that's the key reason that we're here in Canberra today, to try to raise that political awareness or interest. We have no politicians in the room. We invited lots of them. I'm very grateful we have representation from some very key departments and organisations in the room. So we're very happy with the success of the day, even with no politicians in the room. But it's very clear to us now as AGA that our key job is to raise political awareness and interest in geothermal energy. So what can we do to do that? This is my last slide between us and red wine. I'm going to go back to Rebecca's talk at the very start of the day. Rebecca touched on these policy recommendations, but they are laid out literally in black and white in the International Energy Agency's Future of Geothermal Energy report from December 2024. Every one of these policy recommendations is spot on for Australia, even though it's a global report. Move geothermal up the energy policy agenda. Design risk mitigation schemes for early stage project development. Introduce policies ensuring long-term revenue certainty and fair remuneration. Simplify and streamline permitting for geothermal energy. Design policies and regulations enforcing robust environmental and social safeguards. Support geothermal heat applications for residential, commercial and industry use, improve data quality, expand geothermal specific R&D, increase policy focus on expanding geothermal skill sets, and promote international collaboration to develop technical standards for geothermal. So I don't think we can add anything to that list because it's a global list, and this just gives me satisfaction that we're not unique in Australia. We sort of suffer from the same barriers and impediments that the geothermal industry suffers around the world, or not suffers the wrong word, but it faces around the world. Each jurisdiction has its own flavour of how these policy recommendations might relatively float up against each other. But so say this is my final slide. I'm going to leave it on the screen and stop getting in the way of us and alcohol, because we may get kicked out of here in 45 minutes. I'm glad we did not schedule any talks after the afternoon tea break. So I'll leave it at that. Any questions online?